kind of strange. Right. Okay. Yeah, at least it's working here, but I don't know, something is wrong with the remote students because they cannot apparently see the screen. Don't know why. Let me maybe close the lights. Not yet. Yeah, there seems to be some technical issue with this live streaming system for the distance students. So the guys who are at home, I'm not talking to you now, I'm just talking to those who are attending these lectures in Kalmar or in at homes. So there is some problem with this live streaming system. So you will be able to see and hear, I guess. And I will try to upload the lecture slides immediately. But yeah, I apologize for the bad quality of the picture for you guys. So starting with the lecture today, I mean, last time we started about the data structures, and we looked at the tree data structure and the different algorithms. And also I provided you with some examples how to construct and use different and solve different problems using this tree data structures. And today we will be talking more about graph data structures. Can someone describe a bit about what a graph in computer science or in terms of data structure is? Anyone? Yep. Nodes and nodes and edges, yeah. Yeah, in simply, basically a graph, it's a data structure, and it's there are two main things. Every graph is composed of a finite set of nodes, and there are some edges which are connecting the different nodes with each other. I just want to check if I have some questions from the remote students before moving on, because sometimes they have. No, so far not. So as you can see here in this slide, so we have a graph which is composed of 4 different nodes. And what is important is that the number of nodes must be finite. So you cannot have like infinite number of nodes or infinite number of edges. And yeah, and you can represent graph in a mathematical form using the set notations. And the nodes, we usually use nodes to represent the different data items. So for example, if you have different courses, so you can show the course codes or the course names as a nodes. And then if you have some dependencies between the courses, for example, to take one course, maybe in order to take a course in data structures, you need to know some basic programming as a prerequisite. So sometimes you have a dependencies and prerequisites between the different data items. And this kind of dependencies we can show using the edges or the connection between the nodes. So yeah, as a computer scientist, it's generally said that we love graphs, because why we love graphs? Because yeah, we use graph as a computer scientist to solve different kinds of problems. As I said, that one example of graph is that courses, and the courses are the nodes and the different periods are the edges. And you can also consider the different websites as the nodes and the hyperlinks between them, which are connecting one web page to another page is like an edge, and this all you can represent this World Wide Web, the website, the web structure as a graph data structure. And you can also think about the social media, different social media applications such as Facebook, Twitter, and in terms of that, the different user accounts, the Twitter handles, these are, you can represent them. If you want to find out, if you want to solve some problems, you want to find out like how many people are following a person, you can represent that person as a node, and then the followers are the friendships, relationships as an edges, and then you can find. So these all things that can be presented as data items, as a nodes, and then if you want to find out the different associations between them, you can use the graph data structures. So in short, we can say that if you can formulate a problem in terms of nodes and edges, then you can use the different algorithms which we will learn today from the graph data structure to solve these different kinds of problems. Okay, so once you have formulated something as a graph, then you have a very powerful case that you can solve that problem using the different graph data structures algorithms. Yeah, before going to the details in the graph algorithms, we will first look at some basic concepts, terminologies about the graph and the different types of the graph. So the two very basic or the classic types of the graphs are the directed versus undirected graphs. And the fundamental difference between the two is that it depends on the type of the edges or the type of the connection between the graphs. Press the key button. Yeah, yes. So if a graph contains directed edges, and the directed edges means the edges that have a direction. So it's like, for example, if I show you over here, yeah, maybe I don't need a keyboard because we have an example over here. So the difference between these two different graphs is like, in this case, we don't have any particular direction. So these edges are undirected edges. You can travel or move in both directions. So in this case, the graph which contains only the undirected edges, such graphs are known as undirected graphs. And in some cases, so for example, you can consider this as an example of roads between the cities. You can travel in both directions. So in that case, it's like an undirected graph. So for example, if A is representing a vacuum and B is a columnar, and if there is a road between these two, which you can go in both directions, so you can represent this kind of map between the cities using undirected graphs. But in some cases, maybe if you are traveling on a highway or a super motorway or expressway, where you are allowed only to travel in one direction. So, and in that case, we have the graph which contains the arrows or the edges pointing in only one direction. That's called a directed graph. So there is nothing complicated about that. And then we have paths and the cycles. Yeah, so the path is a sequence of so for example, if I say that this is a node and this is an edge, this is one edge, but when there are more than one edges connecting one node to another node, so then this sequence of multiple edges become a path. So in more formally, suppose that node n1 is a predecessor of n2, which means like if we consider the tree data structure, predecessor is like a parent node, and successor is like a child node, which is a predecessor of another node, and so on. And then this sequence of nodes n1, n2, n3 until nk is a path, and the length of that path will be the number of nodes minus 1. Yeah, this is almost the same that we learned in the tree, because in the tree we also have this tree height and tree length and depth kind of things, and then we have this adjacent node. Adjacent node is like In this case, if you look at here, the nodes which are directly connected with the edges, these are the adjacent nodes. If there is an edge from one node to another node, then these two nodes are adjacent nodes. So A and C are adjacent, but A and D are not adjacent nodes because there is no direct edge between these two. So there is a reachable path between A and D, but they are not adjacent. So the concept of adjacencies is like a neighborhood. So if you have a direct neighborhood, then you can see that these are the adjacent nodes. And then sometimes we have cycles in a graph. So cycle means that if there is a path of length at least one or more than one, that begins and ends at the same node. Because if we have a node over here, if we have a graph, let me which has like node A, node B, and node C. So and then if we have something like that, in this case a path starts from node A and then goes from node B and C, and then it comes to an end. So it means like we have a cycle here. So in this case, such kind of paths we call a cycle, and the graph which contains a cycles, there could be one or more than one cycle within a graph, and if there is a cycle within the graph, we call such cycles as a cyclic graphs. And then there is also a simple cycle. The difference between simple and an ordinary cycle is sometimes you have maybe connections like this. So yeah, we have another D, and then it goes back to this node, and from here it comes back. So it means that when you have if you have a repeated node within the cycle, then it's not a simple cycle, because the simple cycle requires that in the sequence or in the path of that cycle you should not have a duplicate nodes. So one node should appear only once. Okay, we will see an example of this over here. So let's say in this case, how many cycles can you find in this graph? Sorry? 4 cycles. Which one? A, C, D, B. Is it a cycle? The first condition for the cycle is that it should start and end at a same node. If you say like A, C, D, B, then it's not a cycle because it starts and ends at a different nodes. Someone else give a try. How many? Sorry? One. Only one. Which one? B. One at a time. Yeah, you can say D, E, F, but it's not ending at D. But then you have to say D, E, F, D. Yeah, because otherwise you are, if you say like this, if you say like D, E, F, it means like you are starting from here, D, then E, and F, and then you stop. If you want to say a cycle, you have to name it completely. D, E, F, and D. Okay? Other than that, if we look at here, A, B, D, you start from A, B, D, and then E, and then F. This is not a cycle, this is just a path. But if we start from the node B, B, D, then you go to E and F, come back to D, and come back to B, that's a cycle. Okay? But it's not a simple cycle because we have d comes twice. Okay, for the simple cycle, it should be only one. So, for example, if you take an example of this one, D, E, F, D, there is no other than the start and the end. Start and the end is okay because that's some necessary condition for having a cycle. Okay. So since we have yeah, at least more than one cycles, yes.
From your example,
Yep.
A, B, D,
A, B.
D, and if you remove this arrow from B to D, is it still directed?
Just a minute. Which arrow you want to remove?
B to D, I mean make it both directions, like undirected, make it straight line from B to D.
So like this.
Is it, no, but not, no arrow.
No error.
Yeah, undirected.
Ah, okay.
I just want to know if this graph, if it's still directed graph, or now it became a cycle.
It's a kind of, if you have a, now you have some directed arrows and undirected. So this is like a mixed graph. In some cases, you have this kind of situation where you have yeah, directed and both undirected graphs. And this kind of graph we call a mixed graph type because it contains both yeah, directed and undirected edges between the nodes. In that case, it's neither directed, neither undirected, but it's a mixed graph type. And if you ask a question if it's like a cyclic, yes, it is a cyclic because you have a cycle. And also, if you consider this one, because you can travel in both, and sometimes you also have a like this loop, yeah, reflexive or kind of thing. So that's also a cycle. Yeah. Okay. And then moving forward, we have some terminologies about connections, and so we call that a graph is a connected graph when there is a path between every pair of nodes. Okay, it could be that it's not really necessarily. So let's see. If we look at an example over here. Yeah, let's see. So connected means if you have a few nodes, yeah, let's see 1, 2, 3, 4, and 5. Is it a connected graph or not? What the definition of connected graph is that there should be a path between every pair of nodes. If you consider this as a whole, as a graph, this is not a connected graph because there is no connection between 1 and 3 and 2 and 4 and also the other ones. So if you want to make it a connected graph, there must be a path from every node to every other node. Okay? And then the opposite of that is a disconnected graph where you have one or more nodes which are not reachable from other nodes. The main property of a connected graph is that from each node there must be a path that you can use to reach other nodes. And on the other hand, if you have one or more components which are not reachable from some of the other nodes, then we call it a disconnected or unconnected graph. And sometimes we also have the weights or the values. I mean, we usually, I mean, in every graph we have some values associated with the nodes. So it depends on what kind of data you are representing using a graph data structure. So you can, for example, if you are representing a map of a city, maybe city names are the nodes value, or the courses are the node values, or the bank IDs or the count IDs. These are the node values. But sometimes we have some information related to the nodes as well. So for example, if these are the different, if the nodes here are different cities, let's say this is Växjö, then we have a Kalmar, and then we have Malmö, yeah, maybe Alvesta, yeah, don't, and we also have yeah, Gothenburg or maybe. And if you want to show the distance between different cities or the nodes, then usually we show that kind of information by labeling the edges between them. So for example, if we say that the distance between Växjö and Kalmar is, let's say, yeah, I'm not accurate, but just any value, 160 kilometers. And the same is for the Malmö, let's say 250, yeah, Alvesta, Malmö maybe 290, any value, yeah, 300. And if we connect with the Alvesta, maybe it's just 15 kilometers. So we can have a values, and then you can also have, yeah, some other information. Let's say what other information could be in this case. We might also have labels for the edges. So for example, the road that connects Växjö and Kalmar, you know, in Sweden we have for every road or for every street we have some numbers. So it's like, for example, road number 25, and the one that connects with the Malmö maybe 23, yeah, 23, Ifira, something like that. So in some cases, but that's an optional thing. It is not really necessarily that every edge should have a value or every edge should have a label. It's up to you. It's up to your requirements. It's up to you, up to the problem that you are solving. If you want to show the relationship and some kind of a distance between the different nodes, or how those nodes are connecting, it's like association between the nodes. So then you can also put that information over here. And in that case, the type of the graph that we use to show this kind of information, we call them as weighted or labeled graph. Okay, if you have only some values assigned with them, a graph with a number or values or the label assigned to each edge is known as a weighted graph. Okay, and it's also possible. I mean, usually we have only one edge between two nodes, but sometimes the problem requires that there are more than two edges or associations or relationships between two nodes. For example, a father and a son, there is a one relationship that you can say that a parent and a child, but then they could also be a partner in a business. So then they are, and if they want to consider themselves as a friend, there is another relationship. And same like a teacher and a student is maybe a one relationship or the association between them. And then if you want to show that if they are working somewhere or if they are playing somewhere, so they might be a colleague as well. And same like maybe you can have more than different roads between Växjö and Kalmar. So there is not only one way. So if you want to go to Växjö and Kalmar, maybe you can go through, yeah, directly from Växjö to Kalmar using this road, or maybe there is another one, yeah, which is maybe longer than. So in this case, the graphs which have more, that allows to have you more than one edges between the nodes, these are usually known as with the name of multi-graphs. Okay. Yes. Question we have.
In the connected graph,
Yeah.
is this one is connected graph because from here there is.
No, this is not connect. Yeah, this is. I mean, if you find a reachable path, if you can. So, for example, the one obvious reason could be like Alvesta and Gothenburg. They don't have a connection between them, but we can go from Alvesta to Gothenburg through Växjö Yes, then it's a connected graph.
And last one you said multi-graph.
Yes.
Even if we don't have those additional paths which you made,
Yes.
we already have from that code to our Liveström to Kalmar. So
Yeah.
we still consider it as a
Yeah, it's usually if you have a direct between not, yeah, you can say like edges, not the paths, because there is a difference between edge and path. Path is when you have a more than one edges, and if you have because if you, of course you can go to Kalmar either this is one, you can say every edge is a path, but not every path is an edge. Okay. So this is one path, and then another one is here, but that involves more than one edges. So normally the multigraph is when you have more than one edges between two nodes. You got it? Okay, good. Yeah. So and then we have also this some other concepts about yeah, the nodes. The out degree, it's simply the number of outgoing edges. Okay, so can you tell me the out degree of the node that is shown here as vectio? How many? What is the out degree of vectio, of the node vectio? Look at again. The number of outgoing edges.
5.
Yeah, 5. I think 1, 2, 3, 4, 5. And what about Gothenburg? 1, only 1. Okay. So the number of outgoing edges is said to be the out degree, and the number of incoming edges to a node, they will be the in degree of that node. Okay. So in this case, if I ask you the in degree of Malmo, 2. Okay. And if it's like yeah, I have already explained the predecessor and successor. So if you have a directed edge, for example, if we have a directed edge here between Kalmar and Malmo, in this case, this is the predecessor, the one from where you start, and the target node will be the successor. Okay. And in tree, we have seen that we have a parent or root node, and we have a leaf node. What was the parent node? The parent node was a node which has no other parents. That was the root node. And the leaf were those without any children. Here, I mean, in the graph, we don't have anything as a root node. That's the one difference between tree and graph, because in graph you have one parent. Every graph will have a root node, but in graph you will have nothing. You can start from here, anywhere. Any node could be a, okay. But a related concept is of a head node and a tail node. The head node will be a node with the 0 predecessors, or the one which has a 0 in degree, okay, because there is no incoming edges. If you have a node in the graph which don't have any incoming edges, then you will call it as a head node. And if there are no outgoing edges, then we call it a, yes. So in this case, if we look at an example over here, can someone tell me the, yeah, can you point out which of these nodes are the head nodes? Any other? No one, I think, because all other nodes have an incoming edge. And how about the tails? Which nodes are the tails? And the tail means that there should be no outgoing edges. G, yeah. So only we have a G. If we remove this edge from the F, then F will also become a, then F will also become a tail node. Yeah. And yeah, and then you can also find out the predecessor and successors of, for example, if we want to find out predecessors of D, so you just find out what are the following links to from D to where we can go from D. We can, from the D, we can go, yeah, to the B, we can go to the, no, these are the predecessors. So from where we can come, the predecessors of D are the incoming C, yes, B, and because there are 3 incoming edges, this one, and this one. So B, C, and F are the predecessors, and successors. Yeah, we can from D we can go to either B or we can go to E. So these are the successors of. So this is simple, nothing something complicated. Yeah, and yeah. We have already learned about tree, but as I told you, a tree is a special case of a graph. Every tree is also a graph, but not every graph is a tree. So, for example, if you look at this graph, we can represent this graph as a tree as well. How can we do that? So just to make you sure, we have a graph A. I'm just trying to draw this for the distance students so they can follow us as well. And so now it looks like more like a graph, but if we draw it another way, like this, A, and from A B, and from C, sorry, and from C we have a, okay. However, the difference between a graph and a tree is that in a graph you can have more than one parents or the predecessors. So, for example, in this case, the C has a, let's say the A is the predecessor of, if we make it like a directed one, like this and like this, we can also have, so in that case, C will have 2 predecessors, A and B, but this kind of relationship is not allowed in a tree data structure, because in tree, every node at max can have one parent node, okay. And yeah, so that's why we say that a tree is a special case of a graph. Yeah, any graph that is connected and contains no cycles. Yeah, and that's also important that there should be no cycles. I mean, if you have something which contains a cyclic relationship, then you can represent it only as a graph, but not as a tree. In the tree, you will not find any cycles. Yeah, so. But I think that's something important that you need to remember about the graph and the tree data structure is that every tree is a graph, but not every graph is a tree. And another important thing is that in tree you have a root node, but in a graph you don't really need to have any specific root node. There could be more than one head nodes. And also, yeah, there are no cycles allowed in a tree, but you can have cycles in a graph. And then we have learned about some tree traversal algorithms. These traversal algorithms these are used to visit the different nodes in a tree or a graph. So we have looked at already these 2 different algorithms for the tree data structures. So today we will look at them, how we can use them for a graph. So we have basically depth first and the breadth first. The depth first is when you go more on a deeper level. You start from one of the, because in a graph you don't have any specific root. So you can pick any node and then you can start from that node and you go down and visit all of its successors. So you go one level down, and if you find another successor, you go down until you get to the tail of the graph, and then you come back. But in the breadth first, in the depth first, you first visit the tails, and then you come to the predecessors. But in the breadth first, you first visit the head nodes, or the parents or the predecessors, and then you go to the childs or the successor nodes. So here is an algorithm for the depth first. So for example, if you pick any node within a graph, and you mark that node as a visited, and you can do that by maybe creating some list or a set. So it's up to you. I prefer a set, but you can consider it as a list, and you add the node that you have visited, so that next time when you come across to that node, you already know that I have already visited this node, so you don't need to visit it again. And then for that node, you check the successors of that node, and for every successor, you check with this list, and if you find that if s not visited, then you recursively call the depth first algorithm. It means that we have not visited it, we need to visit it. But if you have already visited it, then you just ignore it. You don't need to visit it again, because if you have already traversed or already visited a node, you don't need to do it again. Okay? So this is basically, and from this will be more, I think, more clear if we look at an example here. Yeah. So here we have an example. It's the same graph, and as I said that we don't have any here any root node, so we can start basically from any node. If we start, let's say starting from node D. So starting from node D, the algorithm says that when you visit a node, if you start with the node D, then you should add first the D to the list that you have visited, and then you go to the every successor for each successor of D. So what are the successors of D? E and B. These are the two successors, but you can start, you can pick any two of these. So I choose maybe E, and then I add E to the list. So the successors of D are E and B. So I start with the E, add it to this list, and then I check if the E has more successors. Yes, E also has successor G and F. So there is another successors G and F. Okay, so I call recursively the depth first algorithm again on this E method, and on one of these the G, and I go here and I add G to the visited list, and then I check, does the G have successors? No, it doesn't have any successor. So I go back to the E and take another successor of it, F, and check if it has been visited. No, it is not visited, so I add it to the list F. Okay, and then F has a successors, true or false? I'm asking you a question. Does F has a successor? Which one? D. Okay, so if we go back to our algorithm here, F has a successor for each successor, which was the successor D, do here. So D, but when we come to this condition, if S not visited, we check with this list. D has been already visited, so we don't need to visit it again. So we don't call this method again. Okay, so going back here, so D has been already visited, so I don't need to make a call on this. I come back to E. Okay, all of the E successors has been visited. Then I come back to D, from where I have come to the E. And in the D, we have visited E, we have visited D, but we have not visited the B, which is also a successor of D. So I go back to the B and add it to the list, okay, and try to see who are the successors of B, D, but it has been already visited. So when we go the algorithm, we don't need to visit it again. So in this way, we will get D, E, G, F, B. However, if you notice, by using the depth first search, we have only visited few of the nodes, but not all the nodes. Okay? So this means the DFS doesn't guarantees if you use the depth first search algorithms, you may or may not visit all the nodes. For example, in this case, we miss A and C. In that case, then you have to call the depth first algorithm on the not visited nodes once again. Okay? So if I go back to this slides over here, if you want to make sure that you want to visit all the nodes using the depth first search algorithms, then you have to call a new method until all nodes are visited. Okay? So you take a graph G and E, where n is the set of nodes, E is the set of edges, and for each n that belongs to that graph, you keep on calling the depth first search algorithm until all of the nodes have been visited. And it's also possible that in some cases, in the first try, for example, if we started with the node A instead of starting with the node D, in that case, because A has connections with all the nodes, we will have ended up visiting all the nodes in the first attempt. So just make sure that if you are using a depth first search algorithm, and if you have picked a starting node randomly, it may visit all the nodes in that graph, but it may also not visit. It can also visit only few. In that case, you have to start the DFS algorithm on the not visited list. So you have to check yourself which nodes have been visited, and then if there are some nodes which have not been visited, then you have to call the algorithm again on those nodes. Okay, so now the question comes, why this depth first search algorithm is important, and the DFS forest. What is DFS forest? It's when you use when you use the depth first search algorithm again and again to traverse all the different nodes. In that case, you get different trees. So here we get one depth first search tree because it's like a D, E, G, F, and then you get another. So these different the sequence of nodes that you get by using the DFS, we call them simply, because this can be represented as one tree, this can be represented as another tree, and then these multiple trees, as the concept in general life is that if you have a multiple trees, the multiple trees become the forest. So if you have a bigger graph where the depth first search returns in several different trees, and then those several different trees will become a forest. But what is important from here is that you can use the depth first search algorithm for the reachability. If you want to check which nodes can be reached from one node to another, so then you can use the DFS. Okay, for example, if you look at here, if you want to find out which nodes can be reached from D, you use the DFS, and it will tell you which nodes can be reached from the DFS. If you want to find out which nodes can be visited from A, you call the depth first on the node, on that particular node, and then you will get all the nodes that can be reached from that node. That's simple. There is no something complex. But we can also use this algorithm to find out cycles within a graph. If you want to find out, I mean, if it's like a short graph, maybe you can see the cycles by your eye. But if it's like a bigger, thousands of nodes and maybe millions of edges going on, And so in such cases, maybe it's not very easy or smart to find out the cycles manually. And maybe if you have a number of different graphs and visualization, so and finding the cycles manually might be a very not recommended job. It could be a time consuming and also prone to errors. So you might have errors. So then you can use DFS. We will see how we can use DFS to find out the cycles. And also the topological order. We use the DFS to find out the topological order, but we will see them soon. Yeah. Yeah.
The topological order is same as we do it in the trees, like in order terms. Because in the trees, if we have to print out in sorting order, we use depth first search in that.
Yeah, kind of same. Yeah.
And this depth first search,
Yeah.
if we have any precondition, let's say the graph is not connected graph, and then if we will select some random, in that case we also lose some nodes.
We are last sentence.
If graph is not a connected graph,
Uh-huh.
we choose a random node,
Yeah.
and in that case we cannot visit all the nodes.
No, because it's not a connected graph. Yeah.
So is there any condition that before?
But then, I mean, if it's not a connected, but if it's still a graph, then you have to call the depth of algorithm on the unconnected nodes again and again. You got it?
And I have a question about the forest.
Yeah.
What's the relation between the two two trees like the previously slides you showed here? Yeah.
Yeah.
What's the connection with the since so it's the connected graph, right? And what's the connection between these two trees? Should we build up the connection since it's connected?
Yeah, it seems like if you start from here, you get this tree.
Yes.
But if you start, but then there is no. It's not important from the connection point of view. If you want to find out which components are connected with each other, then we have a different algorithm which is coming soon. We call it a connected components algorithms. That will give you the partitioning or the connection between the graphs. But in this case, it's just to describe you that that if you use the DFS algorithm, you might get a single tree, but you can also get more than one trees. And in that case, you just don't confuse yourself with this terminology as a forest. You can just think about it as a multiple trees. Yeah, so it's not something very important. So you just think about forest as a multiple trees. So and then, yeah. So as I told you that we can use this DFS algorithms for these different things. We can use it for reachability. We can use it to find cycles, and then we can use it for topological order. Okay. But before moving to this forward, let's take a 5 minutes quick break to stretch out your legs, and then we continue. Okay. Yep.
Excuse me, sir, again.
Yes,
So
yes.
you said we could put all nodes to set or list,
Yeah.
but isn't it doesn't matter with the sequential or something since if we put in
That's
size-
just want to check that if you have already visited the node or not.
okay,
That's just to
does it
check. Yeah.
matter?
Yeah.
Okay, thank you.
So that you don't check the node again. Because if you that's just to keep track of which nodes you have already visited and which are still to visit.
Okay.
Yeah.
Thank
But you can use any data structure that you want.
But which one is better, listening?
I think it's I would recommend set because then you in the set the duplicates are not allowed. So if you have already visited, then you cannot add it again.
Yeah.
So set would be better choice than a list, I guess.
Thank you.
But yeah, it will be a task in assignment, so you have to think about that. Yeah. Yeah. So the next thing that we have in this graph traversal algorithms, we have another algorithm that we usually use for to find out the cycles in a graph. And so the graph algorithm is named as a post order, and as the name indicates, using this algorithm, we first visit the successors, and after visiting all the successors, we then visit the node itself. Okay, and yeah, we can use it to add the node to a list. So, for example, if you are maintaining a list of nodes where you want to add the new nodes at the end, I mean after the successor, then you can use the post order. And if you also want to assign the nodes a numbering, that every node that you assign should have a number in some order, increment or decrement order, you can use it. And it's basically, there is no such big difference between this post order and the DFS traversal. It actually uses the same steps as we use in the depth first. However, the difference is that we maintain a list of nodes in which we visit the nodes. So this is the methods. This is a general algorithm for this post order traversal. So let's say you have a method with the name of post order, which takes two parameters, node n, which could be any node in the graph, and then you have a list. So for every node for this node, you start by adding this node n to a list, similar to that we have in the depth first. And then for each of the successors of this node S, we check if the successor has been visited. Then we don't need to do anything. Otherwise, if it has been not visited, if it's a new node, then we call the same post order again. And at the end, what we do is, for every node, we have a post order number, that in which order we have visited the node, and we use a simple counter to find out in which position or in which order we have visited that node, and then we add that node to that list. This will become more clear if we use what this is. Oh, as an example over here. So here we have the same the graph, and if we call it with the post order and n and with some list, yeah, here I forget the list parameter. Assume that we already seen the depth first search. Starting with the node A, we get this result. Here we are. This is not post order, but this is depth first, in which we visit the node itself first and then its successor. But in the post order, as the algorithm says, you first visit the successors. So starting from node A, it has two successors, B and C. So here we have a C. So and then we check C. It also have a successor D, and on D we check it also has a successor E, and then we check the E. It also has the successor F, which also have a successor here. But if you took G, so E and F, which has, and then G, and then we'll go back to V. Okay. So when we go to the E, the F has a successor D, but we have already visited the D, so we cannot visit it again. So the first, in the post order, the first node that we visit is the node F. Then we go back to E, we check another successor, G, check it in the list, not visited. We visit this one, go back to the predecessor from where we come, and since it has no any other successors, then we visit this one, F, G, E, and go back to its predecessor. So, and in the predecessor we check, does it have any other successor? Yes, it has successor B, which we have not visited yet. So we visit after D, sorry, before D we visit B, and then we check the B, does it have a successor? Yes, it has a successor. D, but it is already in the marked list. So we come back to the D, and now we have visited all the successors of D. So we can visit D, and then we go back to C and check it doesn't have any more successors. So we visit C, and then we check A. And here we have the numbering. So the first we visit F. So we assigned F a counter variable, which was starting from the 1, and then we were incrementing. So in the order we were visiting, so we assigned the numbers, the PU numbering. F got 1 and so on. The A got 7. Okay. So the basic rule that you need to remember is in the post order, you first visit all the descendants, all the successors, and once you have done, then you go back to the parents and keep on visiting until you have all the nodes visited. How can we use this to find out the cyclic or the cycle in a graph? So here we have the depth first, which returns starting from the A. We get this sequence, and if we do the post order on A, we got this F, G, E, B, D, and from this we got this numbering F1, G2, 3, 3. Okay, and then we have a concept of forward edge and backward edge. Forward edge, if in the forward edge, how can we find if the node if an edge is a forward edge or if it's a back edge? We compare the post order number of the source with the post order number of the target, and if the post order number of the source is more than of the target, then it's a forward edge. The example given is here. If you check A and B for this edge, which is connecting A and B, what is the post order number of A? 7. And what is the post order number of B? It's 4. And since 7 is greater than 4, which means it's a forward edge. And if you have, if that number is less, so for example here, if we check the post order number of B, 4, and then if we check the post order number of D, which is 5, in that case, since 4 is less than 5, so then that is a backward edge. And if in a graph you have at least one or more than one backward edges, then that graph will be a cyclic graph. So we have seen one backward edge. Can you find any other backward edge in this, where the post order number of source is less than or equal to that of a target? If you look at F and D, what is the post order number of F? Sorry, 1. And what is the post order number of D? 5. So 1 is less than 5. Then that's another backward edge. So in simple, if you want to find out if a graph has cycles or not, you find out use the post order algorithm and find out the post order numbering, and then find out if there is any backward edge. And if you find at least one backward edge, you can say that the graph is cyclic graph. Okay. And then we have a topological order. This is the order. Yeah, in this order, we first visit the node in such way that each node appears before its successors. And how can we do that? First of all, use the topological order to find out if there is a cycle or not. And if you find a graph which contains the cycles, it means we cannot find which one is the predecessor and the successor because there is a loop between, there is a cycle. So you can simply say that topological order is not possible because it's a cyclic graph. So you can find out topological graph, which means that we can find out the topological order only if the graph is acyclic. There are no cycles. Okay, and then once again, if we assume that starting from A, here we have the depth first search algorithm. So we visit this node and in this condition, and if we apply the post order on this, yeah, we can get first G, F, E, D, C, B, and if you reverse this post order, you will automatically get the topological order, because it's the opposite of the post order. In the post order, you first visit the descendants and then are the successors, and once you have visited all the successors, then you visit the predecessors. But in the topological order, you first visit the parents and then you go to the, so if you look at here, formally defined topological order is a node ordering like n1, n2, 3 for each node that belongs to the set of nodes, such that any edge from node ni to node j, it must go a forward, which means that every edge should be a forward edge and there is no backward edge. And if there is a backward edge, which means it's a cyclic graph and we cannot compute the topological order. Okay, I hope you understand it. And then, so far we have discussed the different algorithms that were somehow using depth first search. And in the depth first search, we're starting with some node, we go deeper and deeper until the successors. However, in the breadth first, we make sure that all successors are visited before their unprocessed descendants. Okay, so it means that before moving to the descendants, we first visit all the successors. And the algorithm for this is that you can start from any node, pick any node, n, because we don't have any specific route in the graph. And then you mark n as a visited. So similar list, you create a list, and in that list, you add that element that you have visited. Yeah. And then you form a set S0, and in that set you add the node with which you are starting this breadth first algorithm. And then this is your the method with the name of, yeah, you can name anything, BFS in this case, which takes this set S0 as an input parameter, and then within that method you define another set with, for example, if this one is a set S0, then you create 0 plus 1, which is like, yeah, S1 in simple. And in this set, what you do, for each n that belongs to the Si, remember Si here is this S0. So for each n that belongs to this set, we look at all of its successors, and for all of its successors, we check if S is not visited. We have here is that list which is maintaining the visited nodes here, and if S is not visited, we add it to the visited list, and we add that successor to this new set. Okay, and then we keep on until we have visited all the successors, and in the end, when all the successors have been visited and we have computed a new, maybe if n has only one successor, you might get only one node in this set S1. If n has 3 successors, let's say S1, S2, S3, so then maybe S1 will have 3 nodes inside, and we call the BFS recursively on this new set. We will see with an example to get it more clear. So here we have a breadth first, which is starting from a node A. Okay. So in the S1, it means if we are starting with the node A, so first step we add A to the visited list, and we add A to the S0. Here is S0. The next step is for every successors, we create a new set S1, and we add the successors of A, which are in this case B and C. Okay, and then we call the BFS on this set. It means when we call the BFS on S1, we will be looking the successors of both B and C. So, and we create another, and we also starting from the B, we add B to the list, and we find out successors of B, which is in this case there is only one successor, D. So there is no other successor. So we come back, call again on D, and we check the successors of D, S3. What are the successors of D? E and B. However, B is already visited in the visited list, so only E will be there and added into the set list that we have visited. And then we go back to the E, and we find the 2 new successors, G and F. We add them here, okay, and then we go back to the D, and we have already visited them. We go to the C, we already visited them. So in this way, we get this order as a breadth as A, B, C, where we are first visiting the node, then its successors, and then continuing onward D, E, F, G. That will be our breadth first search algorithm. And if we start, for example, here we have started with the node A. If we start with the node D, so in D, we have S0 is equal to D, and then S1 will be the successors of D, in this case E and B, or B and E. And then we have S2, where we check the successors of B, which is a D, that should be already visited, so we don't need to add here. And the successors of E, which are F and G, and then G does not have any successor. F has only one successor, D. However, D has been already visited. Okay, so that's how the breadth first search algorithm will work on. And then next is the transitive closure. And the problem for the transitive closure is that, for example, if you have a graph, and in that graph you want to find out from all the reachable nodes from every node. Okay, so for example, if you have a graph which is composed of 10 nodes, and you want to find out for every node what nodes could be reached. Okay, so, and to find out the reachable nodes, we already know that we can find the reachability using the depth first search algorithm, because if you use the depth first search algorithm, it will point out to you all the nodes that can be reached from that node. However, in this case, we need to create a list of, so there will be not only just one node, but there will be, we want to find out for every node that which nodes can be reached from that node. So in this case, we will create a, if you remember that we have learned the map data structure. In the map data structure, we have a key value pairs. So in this case, the node, each node will be our key, and the list of reachable nodes from that node will be our values. Okay, so assume that DFS node n returns the list of all nodes visited in a DFS. For each node n that belongs to the set of nodes in the graph, create a new list S and call the depth first search algorithm on that node. And every time you call this depth first search node on this node n, you will get a list of reachable nodes. And what you need to do is to find out all the reachable nodes. You can save that list as a map entry where n should be the key and l should be the value. Another important concept in the graph is the connected components. So as we have seen already, that in a graph, it is not necessarily that every node should be connected with every other node. You might have nodes which are not connected, or maybe connected with a few nodes but not every node. So in this case, you might have different parts in your graph. You may have a you may have a one part. If it's a one part, it means like the whole graph is kind of reachable or connected. But and if you want to find out how many partitioning are there in your graph, so in that case we use this connected component concept. So we say that a partition or a part of a graph is a set of nodes such that that set should not be empty. The first condition is to be a partition of a graph, it should not be empty. There must be at least one or more than one nodes over there. And then if we take the union, or if we combine all the different partitions, the end result of combining all the different partitions should be equal to the whole graph. And this condition mathematically says that there should be no duplicates in different partitions. So one node can be only in one partition. You cannot have same node in different partitions. Okay. So for example, if I see this whole classroom and every student has a nodes, and if I make a partition of you, let's see the row at the back end is a one partition, the row in the middle is a second partition, and the row at the front is another partition. So then one student could be only in one partition. You cannot have like one student sitting on front and also sitting at the back at the same time. Okay. And then we have a concept of strongly connected and connected. Strongly connected is when you have a edge between both directions. So if you have a nodes A and B, and if you have an edge like this in both directions, or maybe if it's like this, which can be traversed in both directions, then it's like or it could be a sequence as well. If you have a path in both directions, let's say we have a C here, and then maybe like this. So we have a path from A to B and B to A. In that case, it's a strongly connected because we have Ni and J belongs to the edges. Yeah, and I think it's more, you cannot have, because according to this definition, you cannot have a path. You can only have direct edges to have a strongly connected component. Otherwise, if you have a sequence of paths, as I said before, if you have a path in both directions, like C here, and then here, they are still connected, but they are not strongly connected. Okay. So the condition between strongly connected and connected is there must be an edge between two nodes which are connecting in both directions. But if you have not an edge, rather than you have a sequence of nodes such that all pairs are directly connected, and directly connected means that they have some connections. So in that case, we call them a connected components. Okay. Now, what is important here is that someone maybe asks you a problem that find a graph partitioning, that you should find out the different partitions in a graph in such way that A and B, which are the nodes, belongs to the same set as if and only if A and B are connected, which means that the two nodes can be in the same partition only and only if both are connected. And connected means that there must be a sequence of paths. So they must be reachable from some path. It's not required that they must be strongly connected here. And how could you find out? Here is the algorithm for finding the connected components. And a short description for this is that, for example, let's see, I forget all the times this. So let's say we have this graph over here. Okay, and we want to find out the partitions for this graph. So it says that start by keeping each node of the graph in its own connected component. It means that in the beginning we have 5 nodes. So we start with C1, C2, C3, C4 and C5 and keep everyone in its own partition. So C1 is for the node 1. So far in the beginning it has only 1 inside, and then C2 will have only 2, C3 will have. So start by keeping each node of the graph in its own connected component. Okay, so if you have 10 nodes in a graph, keep in the beginning you keep every graph in a separate partition of its own, and then check out the edges for each edge u, v of the graph. If u and v belongs to the different connected components, merge the connected component of u with the component of v. Okay, so then we take every edge. Okay, in this case here is the edge 1, let's say this edge, and we check that if u and v belongs to different connected components. Do they belong to the different components? 1 and 2? No, because so in that case merge the component of u with the component of v. So in this case we will combine them and remove this partition, and then we go to the other one. Here is another edge 3 and 4, and we find out, do they belong to the, if u and belongs to the different connected components, do they belong to the different connected components? No. So we combine them 3 and 4, and in the end we have this one 4 and 5. We check, do they belong to different connected components? No. So we merge them, and similarly we check with this 3 and 5, so they are already merged. Okay, so in this way you can find out by checking at the different starting with each component in its own partition, and then finding out the edges and checking out if they are belongs to different connected components or not, and then merging them. So what is important is that you find the connected component and merge the two connected components together. Okay, so that was something about the graph data structure. Next, I don't know if you have looked at already or not. The assignment 3 has been now uploaded, and just to see how does it looks like on the Moodle page. If I go here, Hmm. Yeah. So you will have basically in this assignment, you will have basically 3 parts. In the first part, we will provide you some interfaces, and we will require you to implement those interfaces. And we have provided you some description of those interfaces as a Java API, so you can read about that, and also for the node class. Okay, and so at the first thing that you need to do is that you need to implement these interfaces, and it's important that you should follow these instructions for your package name schema. For example, your implementation should be in your own package, and you can download these different interfaces from here. So if you look at this here, so here you have the different interfaces. So yeah. Maybe we can look at here. So here we have this all the interfaces that I provide you for the graph. So and here you can see the different methods, and we can look at these different methods over here as well. So in simple, in the part 1, you will require to implement few graph interfaces. The main interface is the directed graph interface. It provides you with the method. We will look at what methods are there, and then you will get a node class, abstract class, and you will be required to implement this class. And you can find out the details about what those methods are supposed to do in the method requirements. And we also provide you with the JUnit test case just to check out your implementation. So this is very important, and you will get these test cases together with the assignments, the interface definitions. And whenever you implement one of these classes, either the directed interface or the node class or the different algorithms, so you keep on checking your implementation using the JUnit test case. So that if that's the first requirement, because if your submission doesn't pass these test cases, it means that you will not be able to pass the assignment. And in the second case, we will ask you to use implement few algorithms. And in those algorithms, we have this depth first, post order, cyclic, topological, breadth first, transitive, connected components. You have already seen these algorithms as a pseudocode, but now you have to implement these algorithms in Java. I will come later on. I will describe what is this GML. This is a markup language to create graphs and visualize the graph in a file format. So, and then in the third part, we will ask you to compute the time complexity. And we will talk about time complexity in the next lecture. What is the time complexity and how you can compute the time complexity. And you will require to compute the time complexity for 4 methods. For your depth first method, the implementation of your depth first, and the implementation of your breadth first, and transitive closure, and this method which is about connected components. And some details about the graph interface. The interface that we are asking you to implement, it basically implements a directed graph, which means that there will be one-way arrows, one-way edges, so from one node to another node. And each node will be represented by this graph.node abstract class, which you get together with the assignment. And it should be a generic type. You already have learned the generics. And 2 nodes representing the same item cannot be added. So it means that the no duplicate nodes are allowed in the graph. So if someone tries to add a node with the same item value which has been already added, so it should be ignored, or maybe some exception should be thrown. And the 2 node items are the same if this method returns true, equals method, or if they have a hash code value is true. And yeah, and we don't allow the multiple edges between two nodes. So there could be only one edge between two nodes. So if you have a node A and node B, so it means, for example, if you 3 and 5, you can only have one edge. And since it's a directed graph, so that edge also be in some direction. And you cannot have more than one edges between the two nodes. So there will be only one edge allowed. And we don't provide you with a specific edge class. Yeah, in the graph and the node, if you see, the edges are handled by using successor and predecessor field values. So maybe if you want to look at here in the node class, I think, yeah, it has the item, and yeah, we ask you to handle this. Yeah, the item is the value that has been stored by a graph. And if you go here, yeah, there are no specific fields, but you can handle these edges by creating a list of successors and predecessors. Yeah, and we provide you with the Java API, and you can find out in the assignment page, for example here. So for every, for example here, you have all the details, what is this class and what does the method does. For example here, if you see this add edge for, this method is used to add an edge from this node E to this node, from to E. So it can take two parameters, and this method is used to add edge. This is used to add a node, and if you want to get all items, so you can just read on these details, and if you have a question, of course, you can contact Maria, the assignment assistant. And yeah, so what next? So here is just a simple overview of this directed graph interface. So it's basically a generic type of interface. So it means it can be created integer values or string values. So, but if you do it on integer values, that will be enough. And yeah, it has this add a node for, which takes an item. Of course, if it's an integer, then this item should be integer value as well. Get node for, so that will, if you pass a value, and then that method should return the node that contains this value. And you can get the iterator, yeah, and the tail count. It will return the number of tails, the nodes that are tail nodes in your graph. Edge count method should return the total number of edges in your graph. And yeah, if you want to remove an edge, yeah, you can use this method. And the toString method should provide some suitable, nice looking representation of your graph in a string format. So here is just an example for you. So for example, yeah, if we want to create a graph of type integer, so you can use this kind of declaration, directed graph integer G, and my graph, this is supposed to be my implementation or your implementation. So this is an interface, and this is the class that implements, because you know that we cannot create objects or instances of interface. We can only use to refer them. This is your implementation, I believe. And then you can add nodes in that graph. This is just an array of integers to add values for the nodes. And yeah, so here I have, but when you create a graph, it is an empty graph. There are no nodes in it. Then you add nodes in the graph by calling add node for this value, for this value, and this value. So we have added 3 nodes. So it means that yeah, it could be like this. It looks like that you have now added 3 nodes, 0, 1, and 2. But there are no edges yet, because we have not added edges. To add edges, you use the method graph.addEdge for, and this is from and to. So we want to add, this method will add an edge from node 0 to node 1. So from 0 to node 1, and then from 0 to 2, and then from 1 to 2. Okay. So this can you can add edges using these methods, and also you can use this add edge for method, and this add edge for method, for example, it tries to add an edge from node 1 to 3. However, the node 3 doesn't exist. In that case, it should create a node as well. So before adding an edge, if a node hasn't been not found, it should create a node and then an edge. So in this case, it says that this will do like that: create a node and then add an edge from source to that node. Okay, and then here is the abstract node class. So similar to the graph, because the graph supports generics, so that's why we also assume that the node class also should support the generic values. And the E item, this is the value of node. So this node class is actually representing these nodes in your graph, and this item will be used to store these values. This is your item actually. And then you have number, temporary integer value to use in the algorithm, and the constructor should be used to assign these values to these the node items. And string out degree should return the out degree, the number of outgoing edges. And so in degree, and has predecessor, it should return true or false if a node has a predecessor or not. And if you know that if a node doesn't have a predecessor, it means it's a head node. And if it doesn't have other way around, it might be a tail node. And so here you can check out is head, and it checks in degree, and if the in degree is equal to 0, it means it's a head node. Okay. Yeah, here are some hints about your implementation for the my node class. As I told you that something important is that you should decide on what kind of information that you want to store in your nodes, and which fields do you want to use. So you already have a field in the abstract class for the value item, so maybe you don't need it for the values. But if you want to maintain the predecessors and the successors, so maybe you need something for the predecessors and the successors. Okay, so this is my implementation, but of course you can have your own implementation. But this is just to give you an idea that how can you use to implement this node. So you should maybe say a class my node which extends the abstract class nodes, and then you provide all the implementation for all the different methods that have been defined in the abstract node class. And similarly, there's some code from my implementation of my graph. So, and this class should implement the interface directed graph. And here we have I use head and tails, just to find out that, and you can, I don't know which data structure you want to. I'm using the set, but you can use any other data structure if you like. I mean, but keep in mind that it should support all the requirements. If you decide to use the linked list, hash map, or any other, I'm okay with array list or anything, but it should support all the properties that are required by different directed graphs. Okay, and so you can, and then I talked about the GML. It's the graph modeling language. Basically, it's like an HTML kind of markup language that you can use to display or to store graphs in a file format, and you can read more about GML on this link. So, for example, if we try to open this one, let's see where we just go. Yeah, it's taking quite time. Yeah. So, and if here you go, here you can find out what is GML, and you can see some more details about the GML as here, and you can also yeah, I think we have an example over here for the GML. This is just some kind of a description here. The important part is here. The GML, it's basically represent a graph in a text format. So to represent a graph in a text file, you start with the graph keyword, and then with the square bracket, and then you define all the nodes. If you have like 10 nodes in your graph, so you use the node, and then to assign every node an ID, you use the ID keyword, ID0, and this label statement to label that node, and then you use this graphics. Yeah, that's you want to show that how the node should look like, rounded rectangle, and this is if you want to fill the colors in the nodes, so on. So if you have 2 nodes, maybe you can define it here, or once you are done with the nodes, then you can define the edges using this edge block statements. And in the edge, so for example, if you want to add an edge from node 0 to node 1, so you specify 0 as a source and 1 as a target, and then you can also specify the graphics for that node, and the width and line, and also so the arrow means like directed edge. And to see these graph files, there is a tool with the name of Y-file YED, and all these GML and what is important is that you should save your files for the graph files in a file with the name of .gml extension, and yeah, so. And this tool you can find out here, and it can be downloaded and can also be used as a live. It's a editor to visualize the different graphs. So yeah, you can download it here, and you can also use it live here, but I recommend that you should download and install it. And yeah, so that's it. And if you have if you need more help about GML, or how you can use YED, because when you open a GML file in this YED tool, it's important that the YED tool provides you with the different layouts to view a graph. So for example, hierarchical, circular. In the layout menu, you should maybe when you first open a GML file in the YED, you will not see the whole graph. Maybe you would see only one node. But then you have to go to the layout menu, and from the layout menu you have to select hierarchical, circular. In most cases, if you choose a circular layout, that will be good enough. And this part is only just to see, because when you are creating your graph in a Java programming language, in a code, it's not very visible. You know, you are just writing like add edge for, add node for. It will not be visible. But if you want to see that how your graph looks like, you can you can write a Java code to create the GML files. So for example, you can use the file API, file writer, and in the file writer you should generate your code to write these GML files. You will see more details about this GML thing in the here. How should this GML, yeah, you can also find some details over here. That extends abstract class GML. Yeah, so these methods about the dump and the 2 GML files, so you can read more on here. And if you have questions, yeah, Maria knows a lot about GML and YED, so just contact her if you have questions. Okay. And yeah, and you can further read about the graphs and these different things, yeah, in these different books and chapters. And of course you can yeah, use the Google and Wikipedia to learn more about. In the next lectures, as I said earlier, that we will look about the algorithms and the different algorithm description languages, and then the focus will be more on time complexity, which is also part of the assignment 3, the third part. So that's it for today. So see you next week. Okay, goodbye.